Hey everyone, welcome back to Probability Theory. This will be lecture 21 of the course, and in this section we're going to discuss a very cool little theorem for discrete random variables, and that theorem is called the Chebysheff's theorem, and it's something that is notoriously difficult for students, but hopefully we can make it simple and straightforward. Let's go ahead and jump into it. We'll call this section 2.10. Chebysheff's theorem for discrete random variables. So the idea behind this theorem is that it's basically used as a means for determining the lower bound for the probability that a random variable is going to fall within a certain interval. And so let's state the theorem, and then we'll go through some examples and talk it through. So this is again, of course, called Chebysheff's theorem. It's based on an inequality that we'll talk about in a second as well, which is called Chebysheff's inequality. We'll start with the theorem, and then the inequality is very similar. So let's let y be a random variable. Let y be a random variable with mean mu and finite variance sigma squared. Okay. Then for any positive real number k, we have the following. There's kind of multiple ways to express it, so I'll write two different ways down. The first way is to say that the probability that the distance between the random variable y and the mean, that's all that is, the distance function, the probability that y minus mu is less than k times the standard deviation sigma. All right, so here you've got the distance between the random variable and the mean is less than k times sigma. That probability is going to be greater than or equal to 1 minus 1 over k squared. Okay, so this is basically saying the probability that the random variable y is within k standard deviations of the mean is greater than or equal to 1 minus 1 over k squared. Okay, so that's one way to express it. Another way to express it is to say probability that y minus mu is greater than or equal to k times sigma, i.e. it's outside of k standard deviations. That probability is less than or equal to 1 minus k squared. So it's really kind of the same thing. You're either expressing the probability that the random variable is within k standard deviations, or you're expressing the probability that the random variable is outside of k standard deviations. Okay, so remember, k is a constant. Like 2 or 3, k equals 2, k equals 3. So what we're saying here is that, let's write it out here. I want to make sure, because a lot of times people just get hung up on the notation here, but it's really not that tricky. So we'll take the second meaning here. So what do each of these pieces mean? So remember this part here, which is the part that people tend to hate, undergraduates tend to hate this. This is just the distance between the mean and our random variable. So it's just the distance between y, our random variable, and the mean. That's all this is. Okay, and what are we saying here? Well, all we're saying there is that is greater than k standard deviations. Is more than k standard deviations. Right? So we've seen that. If you've taken some elementary statistics, you'll definitely know 1 standard deviation, 2 standard deviations, 3 standard deviations. So all this is saying is that the probability that the distance between the random variable and the mean is greater than k standard deviations. And what's really nice about this is that that k carries over here, and we're saying it's less than 1 over k squared. right? So that whole probability has to be less than 1 over k squared. So for example, if we're talking about 4 standard deviations, that probability would be less than 1 over 16. If we're talking about 2 standard deviations, it's 1 over 4, right? So it's very simple, actually. It's a really simple expression. It's just that sometimes people get hung up on the way it's notated. Okay, but that's all it's saying. And so this is, as I said, it's based on a slightly simpler inequality. I don't know if it's simpler, but a different inequality. And that inequality is frequently referred to as Chebysheff's inequality. And it just says that the probability that x minus mu is greater than or equal to k, that's less than or equal to sigma squared over k squared. Okay. And I think just kind of show you how this derivation comes from, let's replace all the k's with c's so I can do a proper substitution here. Okay, so I'll just kind of, instead of k's, I'm going to write c's, and we're going to kind of forget about that. Right, and then the idea is I can just replace c with k times sigma. So replacing c with k times sigma, of course, then I'm going to get what's up above here. So the probability that x minus mu is greater than or equal to k times sigma is less than or equal to sigma squared over k times sigma squared. Okay, and so then, of course, this is the theorem above. Probability that x minus mu is greater than or equal to k sigma is less than or equal to 1 over k squared. Okay. All right. So again, like, not to get too hung up on that, but you'll frequently see, instead of seeing the theorem as I wrote it out up above here, you may see it in this form, which is frequently just called Tchebysheff's inequality. It's similar, very obviously, as you can see, it's the same thing. It's just how you express it. Okay, so for example, let's say we let k equal 2. Then what we're saying here is that the probability that x minus mu is greater than or equal to 2 standard deviations, that's less than or equal to 1/4. And as k gets larger, the probability that x minus mu is greater than or equal to 3 standard deviations is less than or equal to 1/9, right? And so on. And of course, the further, the wider you make the interval, then the smaller this ratio becomes. So the probability that x minus mu is greater than or equal to 10 standard deviations, right? So 10, so it's outside of 10 standard deviations. That's going to be very small indeed. It's going to be 1 in 100. Right? So we're just squaring k. So this is for when k is equal to 10. Okay, so just very simple way to relate this. Okay. So the basic idea here is just that if the variance is small, right? If the variance is small, then the random variable x is unlikely to be very far from the mean. Okay, and that's especially evident when we look at it from the lens of Tchebysheff's inequality here. So when the variance is very small, right? Say the variance is 1, then the probability that the random variable is very far from x is going to be small. Okay, so that's the idea with Tchebysheff's theorem. Let's take a look at a real example of where this is useful. And it's useful in a lot of ways, not just applied examples, but also it has a lot of theoretical value, which you'll see later in the course as we start to use it in proofs and things like that. But here's an example where it's actually of practical value. And so this is from the textbook. The number of customers at a store, is found to have a mean of 20 and and a standard deviation of 2. Right, and so we've got a mean of 20 and a standard deviation of 2. We don't really know the probability distribution, but we'd like to say something about the probability, about a certain probability. So we don't know the probability distribution. Right, meaning we don't, we can't say that for our random variable being that y equals the number of customers at a store, we can't really tell you what the probability distribution is precisely. We do know that empirically we identify a mean of 20, and we do tend to see a standard deviation of about 2. But what we're interested in is we'd like to know the probability that the number of customers will be between 16 and 24. We'd like to know the probability that the number of customers is between 16 and 24. Okay, but again, we don't know the probability distribution, so what can we do? Right, so we'll think about it like this. We'll say y is a random variable. It's the number of customers. In this case, I can't say that y has a particular distribution. I don't know. I do know that the mean appears to be 20 and the standard deviation appears to be 2. Okay, but I don't know any more than that. So how can I identify the probability that y will be between 16 and 24? Well, as you can probably guess, I'm going to use the theorem, Tchebysheff's theorem. All right, so what does Tchebysheff's theorem say? And we'll use this version of it. We want the probability that y minus mu is less than k times sigma, and that probability is going to be greater than or equal to 1 minus 1 over k squared. That's what we're going to use. Okay, and so if we remove the absolute values here, we can rewrite this as the probability that mu minus k sigma is less than y, which is less than mu plus k sigma, and that's got to be greater than or equal to 1 minus 1 over k squared, right? So here I'm just saying the distance in absolute value is less than k sigma, so instead of writing it like that, I can write it like this. I can say mu minus k sigma is less than y, which is less than mu plus k sigma. So that's still an interval about mu, a k sigma interval about mu, right? So that's just another way to express it. Now, if I let mu equal 20 and sigma equal 2, then in order for this bound to equal 16, so basically 20 minus k times 2 equals 16. So you solve that and you can see that k needs to be equal to 2. And it's the same up top here, right? So 20 plus k times 2 equals 24 implies that k equals 2, right? So I can let mu equal 20, sigma equal 2, then k must equal 2. And I can just plug all these values in and see what's going to happen. So the probability that 20 minus 2 times 2 is less than y, which is less than 20 plus 2 times 2. That whole thing is greater than or equal to 1 minus 1 over 2 squared. Okay, and so that's basically the probability that 16 is less than y, which is less than 24. That's greater than or equal to 1 minus 1/4, otherwise known as 3/4. Okay, and so while we haven't found a precise probability, what we are saying is there is at least a 75% chance that tomorrow's customer count is between 16 and 24. Okay. So that's a practical application of this theorem. And now remember, we said that really the idea here is that if sigma is small, then the random variable is not likely to be very far away from the mean. That's intuitive, right? Let's see what happens when we reduce the standard deviation in this case. So let's say instead that mu is 20 and sigma is 1, right? So reducing the variance, reducing the standard deviation from 2 down to just 1. And so the same calculation, right? We have probability that mu minus 2 sigma is less than y, which is less than mu plus 2 sigma. That's going to be less than or equal or greater than or equal to 1 minus 1 over k squared. Sorry, I put 2 here. I meant to write k. Apologies. Okay, so that's a k. Right, now in this case, mu minus k sigma, right? In this case, that's 20 minus k times 1. And if that's equal to 16, then that means k needs to be 4. Right, and similarly, 20 plus k times 1 equals 24 implies that k is equal to 4 as well. Right, so k has to go up if sigma goes down. And so what I have here is the probability that 20 minus 4 times 1 is less than y, which is less than 20 plus 4 times 1. That whole thing is greater than or equal to 1 minus 1 over 4 squared. Okay, so just plug in those numbers again into the thing. So I've got the probability that 16 is less than y, which is less than 24, is greater than or equal to 1 minus 1 over 16, which is equal to 15 sixteenths. Okay, and so with the smaller variance here, moving from sigma equals 2 to sigma equals 1, when I move the variance, my probability gets way more certain, doesn't it? Right, so now I can say that, with almost certainty, the probability is greater than 15 out of 16 that tomorrow's customer count will be between these two values, right? Because my variance is very small. Okay. All right. Very good. And so I think that's a good place to stop with Tchebysheff's theorem. And next lecture we'll do some problems and examples to kind of round up our discrete random variable section. And then after that we'll be moving into continuous random variables. So until then, take care everyone.